Shall we start?
Yes, please. I think it's past the hour, so.
Okay. So can everyone see my PowerPoint?
Yes.
And if I do this, can you see the data?
Yes, sir.
Okay, thank you. So it occurred to me that I needed to discuss the assumptions of these few tests we're going to talk about today, along with the tests. Otherwise, I would be committing statistical malpractice, because the test results, the p-values, the confidence intervals, the effect sizes mean nothing at all if you violated the assumptions of the tests, because the tests are based on distributions, and if you choose the wrong distribution based on a failure to equilibrate standard deviations across groups, say, or you have some outliers, or you have a nonlinear relationship, and then your results mean nothing because they don't conform, your data don't conform to the assumptions. So just going through those very briefly, and some of them are much more voluminous and complicated than I'll discuss, but we'll start with the t-test. Someone had asked to see how to perform a t-test in SPSS. So in order to justify the use of a t-test, we need to have continuous data, and that means interval or ratio, i.e. the distances between the measurements are the same, are equivalent. Independence of observation, you cannot have any one subject represented more than one time in the data set that you're analyzing. If you have outliers in the data, those are going to skew your statistics, so we always pay attention to those. And the t-test is based on the assumption that the data, the raw data for each of the two groups, are approximately normal. The t-test is used to compare two continuous data sets or two continuous variables. And then finally, homogeneity of variance, where we assume, or the statistical test, the t-distribution is based on the assumption that the standard deviations or the variance across groups are identical. So let me go to the data set. And before we start anything, just to get a sense of what the data look like, I'll always run what we talked about last week, this explore statistic. What I have here is a data set in which I was trying to predict FEV, or forced expiratory volume, as a function of age, height, sex, and whether or not the person had a history of smoking. These are just categorical variables I formed from age and height. And then a second, if you, I sent this data set, if you want to open it, you can go along with me. You won't see this variable because it just occurred to me 3 minutes ago that I needed to show you how to also run a matched pairs or a dependent samples t-test. So you won't see this, but it's we'll use it in one of the examples. So the first thing I do is I'm going to go through, pull all of these variables, the ones that will enter my analyses at some point. And then I'm going to turn on histogram. I prefer it to stem and leaf. It's more meaningful to me. So this is going to give us a sense of the kind of data that we have. I'm going to turn off statistics just because I don't want to go through those right now. But this will give us the plots. We see we have 654 cases. Our primary outcome variable, forced expiratory volume, is not perfectly normal. It's a nice distribution, but you can see it's slightly skewed to the right, positively skewed. This is the box plot version highlighting these outliers to the right. The same for age. We have a slight skew for age right here on the right side, ranging from under 5 years of age to almost 20 years of age. And the equivalent box plot against some outliers. And height tends to be slightly left skewed here. So again, we have a non-normal data set that we're dealing with. So we can accommodate that. These are just histograms of, this is a binary variable for male, female. And for, you can see very few, 1 indicates they smoked, 0, they didn't smoke. So we have very few smokers, which you would expect in this age group. And these are just the categorical variables that I calculated from the continua, just to display the data in a more in an alternative manner. And that's just my second measurement of FEV, which I calculated. These are not real data; I made those up. But let me show you one thing I didn't turn on, because we did talk about that, and I want to show you right here. We probably should upfront test the normality of the data, although we have a relatively large sample. It's important also to look at the degree to which our distributions for the continuous variables are depart from normal, because we may have to accommodate that at some point. So you can see if we go right here, the second table, that by default, it runs the Kolmogorov-Smirnov and the Shapiro-Wilk test. The Shapiro-Wilk test is thought to be a little better for small distributions. This is a relatively large sample, so I would tend to rely on this. And it tells me that in every instance for the variables, the continuous variables of interest, the FEV, age, height, that I have significantly non-normal or skewed data. And the reason I bring that up is that a lot of the tests that we rely on tend to specify as an assumption an approximately normal distribution in order to interpret the test statistics accurately. So what we're going to do now is we'll go back to the data, and we're going to go to analyze. And we're going to go to compare means, because that's where you're going to find the t-tests that we use. There are multiple t-tests, one sample t-test that you can run with data from one group as long as you have a reference, mean and standard deviation. Well, you don't even need a standard deviation. As long as you have a reference mean against which you want to compare the data, you can run a one sample test, which will tell you if your sample differs significantly from a reference that you have. The independent samples test right here that we've just been talking about, in order to run the independent samples test, click on independent samples. Our outcome variable is FEV, forced expiratory volume. And as a grouping variable, let's use sex to see if it differs across males versus females. Now, when you enter that, it's going to ask you to designate the values for two categories within your predictor variable. So you can see here is my predictor variable, what I want to use. And I've got a label, a value label on those female and male. If you want to know, if you don't remember, which I typically don't, how you coded them, you can look up here, which will tell you that females are 1, males are 2, or right here, you can simply turn off the value label right there, which is kind of handy sometimes. So I turned it off and I see that my variables range from 1 to 2 in value. I'm going to turn it back on. So that means that if I want to compare males to females, I have to tell it I want to compare groups 1 and 2 right here. And then we always look at the options, and those, the 95% confidence interval is what we use for a p-value, a criterion value of less than 0.05 to as a cut point for significance, so I'll leave that as it is. Bootstrap is something that we use sometimes with smaller samples in order to get a more confident, a more conservative 95% confidence interval. We won't jump into that because that gets into a more advanced discussion. But I'm all set up to go. And you can see here that I could also, in fact, I will run age and height, both continuous variables, to see if they differ across sexes. So all I have to do now, since I've defined my groups, is hit OK. And we get this output for forced expiratory volume, age, and height. And here are our descriptive statistics. You can see that males tend to have a slightly higher FEV than females. They tend to be slightly older, 10 versus 9.8. And they tend to be slightly taller, 62 inches versus 60 inches. But here's the results of the analysis is provided right here. And in interpreting this, you want to look right here, the t-test for equality of means. So you know that I mentioned that one of the assumptions for a t-test is that the variances across groups be equal. So this Levine's test is testing that assumption right here. So it's part of the output. And it's telling us that the variances for males and females, and what it's testing is right the variance is the square of the standard deviation. But you can see that for some reason, I don't remember why that is, that the variability of the males is definitely considerably higher than the variation of the females. So what this is telling us is you've got a problem right there. If this p-value is less than 0.05, it says you have not met the equal variances assumption, so you have to adjust the analysis. What it does is it adjusts the degrees of freedom that it uses for the lookup table right here. So it tells us, do not interpret this because it's a bad statistic. Instead, assume that the variances are not equal right here. So if this p-value, again, is less than 0.05, we will not assume equal variances. So that means we interpret this value rather than this value. And you can see they're identical. It doesn't really make any difference. But just in terms of following good practice standards, you would use this, you would interpret this test because the variances are not assumed to be equal because we've shown they're not. And what that will do is it changes the degrees of freedom a little bit. It penalizes you a little bit. The mean difference is obviously the same. The standard error is changed though. You can see that we have a smaller standard error here. And that adjusts the confidence interval so that we could now interpret this to mean that there is a statistically significant difference, p less than 0.05, because I left the 95% confidence interval as the default. There's a statistically significant difference between males and females in forced expiratory volume. Okay, so we have the value of the t-test, if you have to report that in your manuscript, the degrees of freedom. And the way you report this is not p equals 0.000, although I've seen a lot of people do that. We more typically report this result as p less than 0.001. That's more or less standard in the journals. You can see that for age, we don't have a problem right here with the equal variances assumption. So that means we can interpret this line. And this is telling us there is no difference on average in age across males versus females right up here. And for height, we have a statistically significant difference. But again, we have to look back here to see if we've met this assumption. And we've already said we don't. A lot more variability for males than females. So in that case, we interpret the second line. Equal variance is not assumed right here. And again, we find that the p is less than 0.001, so we can conclude that there's a height difference between males and females. course, the most interesting of these is the difference in forced expiratory volume. Does anyone have any questions on that? So that's pretty straightforward. Again, you go to compare means, choose independent samples t-test, set it up, and define the groups, and choose whatever options you want and bootstrap the data if you have a small sample set to get a more accurate estimate of the confidence interval or the variability around your mean estimates, your mean scores.
I have a question. The group variable, is that the predictor? Is that what you mentioned?
Yeah. In this case, I'm that would be the grouping variable is I'm using that to predict these values right here. Yeah. Anything else? Now, if I have a grouping variable, say, if I had a grouping variable here, I was wanting to look at forced expiratory volume, say, across H categories. I think I have 3 of them there. Yeah, I have 3 H categories, but here I can limit that to an analysis. It has to be 2 groups because it's a t-test. So I can say I've coded my H category variables 1, 2, 3. I could just choose 1 and 2 or 1 and 3. That's why they have you choose right here. So it lends a little flexibility to your analysis capabilities. So I'm going to get rid of that. And then we'll talk a little bit. Okay, that's what we call an independent samples t-test, where you have no common subjects across the 2 groups. And then we have a dependent samples t-test right here, where again, the dependent variable must be continuous, i.e. interval or ratio, but the 2 groups must be paired. You must have 2 values for each row in the data set that represent a common instance, in this case, a common person. Again, no significant outliers, because those will skew the results of the analysis. And then in this case, we would look at the histograms or the distributions for, say, FEV and age, and each of those must be approximately normally distributed, which they are. In this case, we don't care about that. The only thing we care about in terms of the distributional assumptions is that the difference scores be somewhat normally distributed. So what this test does is it takes a difference score between time 1 and time 2, or measurement 1 and measurement 2, and then it evaluates the statistical significance of that difference score. It doesn't care about the distributions of variable 1 and variable 2. So this is the one I just created a little bit ago. Right here, I needed to have a paired measurement of FEV, and let's say that I took FEV at time 1 and then I took it 6 months later, and I wanted to see if there was a difference between if FEV had increased or decreased over the time period. So to do that, I would go up to compare means again. In this case, I'm looking at a paired samples test right here. So what I would do is I would enter my FEV at time 1, hold down my control key. This is the easiest way to do it. And then move those over right here. My options are the same. I'm going to stick with the 0.05 for significance. And I'm not going to bootstrap this one because it takes a little bit to do that. But that's all I do here. And I can run up to like 50 different pairs at one time if I want. And I've done that before. It arises on occasion where you have many, many pairs of data. So I say, okay, and here's my output. And I see that for FEV time 1, 2.6 on average, at time 2, 2.9, so that you see a definite increase here. with a mean difference of 0.27 between the two measurements. And we see here, again, it doesn't care about the normality of the two groups. It just cares about the normality of the difference scores. So here would be my p value, again, p less than 0.001. And the thing is, when you have 654 data points, as I have here, you can find statistical significance with even relatively small differences, which is what we see right here. So that's all there is to the paired samples test. Any questions about that? Now, very frequently, I've seen more commonly recently that editors and reviewers will insist that you report the results of the Kolmogorov-Smirnov or the Shapiro-Wilk test, the test of distributional normality, along with your test results in order to show that you have tested the assumption of normality. So in that case, you would report that along with the p-value of less than 0.001, but someone will come back, since we did show that we have, at least for the independent samples, that our data were somewhat non-normal. They will come back in all likelihood and they will say, your data are non-normal. You need to fix that. So the way we fix that is we use a non-parametric, what's called a non-parametric analog of a t-test. And we can do that two ways. And it's very easy to do. There is a wizard in SPSS that allows us to test one sample, as we talked about, independent samples and paired or related samples. So just, I'll run you through that very quickly. And now this one, I mentioned last week that when you use a wizard like this, looks like that, it's going to insist that you have, in this window right here, the variable window, it's going to insist that you have an appropriate measurement scale assigned to the variable. So for an independent samples test with two groups in which the data are somewhat skewed, we can use this wizard and it will choose the right test for us right here. Automatically compare distributions. That's saying it's going to look at the distributions to see if they're normal or not, and then it's going to choose the appropriate test for you. Or you can go in here and customize the test. By default, what it's going to run is the Mann-Whitney U because we have two samples. So I'm going to leave it on automatic. So all I have to do here, I'm still interested in forced expiratory volume, and I'm interested in comparing across males and females right here. So it does all the work for us, basically. It looks at the distributional assumptions and decides what's the appropriate test to run. And it also gives you some nice output here. And it says, as we've already concluded, you should reject the null hypothesis. Gives you some nice descriptive statistics and statistical values. It gives you histograms that show the frequency of FEV for males versus females right here, so you can see where the differences lie. Now, the difference between a Mann-Whitney U test and a t-test is that the Mann-Whitney U tests relies more on the median, the 50th percentile value, than it does the mean, the arithmetic mean. And that's not perfectly accurate, but it's pretty close. What I said is not perfectly accurate. Then it gives you histograms so you can see the distributions of your data right here. So this one's kind of nice. You just have to take care to make sure to dot all your I's and cross your T's before you actually analyze the data. Because if I had coded for whatever reason, if I had coded this as a nominal variable, it would come back and say, I can't run that. You need to fix your data first. So if, when I have a sample this large and I have a slightly non-normal data set, I'm really not too worried because I know I'm going to get the same result from a t-test and a Mann-Whitney U. But in all likelihood, if you report your distributional tests, the Kolmogorov-Smirnov or Shapiro-Wilk, it's going to, a reviewer or the editor will come back and say, well, you ran the wrong test. Well, you can see here, it's a very easy fix. And then for the, if we wanted to do a paired t-test type setup here, then what it's going to do is if, let's see. So I wonder on forced expiratory volume here versus my second measurement of forced expiratory volume. So it's going to, it says select only 2 test fields. So I'm running essentially what is a matched pairs or a dependent samples t-test here. But it is the non-parametric version, which doesn't rely on distributional assumptions. It's called a Wilcoxon signed rank test right here. And again, you know, with this large of a data set, it's telling us that we have a statistically significant difference between FEV measured at time 1 and measured at time 2. And it gives us a nice little graphic here of the positive versus negative differences. That is, if you subtract one from the other. And it gives us, again, it gives us a nice histogram for FEV at time 1 and FEV at time 2. So this is, I typically don't use the wizards in SPSS. There are old-fashioned ways of doing it that I'm used to, but this is kind of nice. It gives you some nice graphics. So any questions on that? So if you run into a problem with a reviewer editor, you say, okay, well, I'll run a non-parametric version and we'll be done with it. And you'll get this exactly the same answer. In fact, say for a independent samples t-test and a Mann-Whitney U, the non-parametric version, the non-parametric version using the median rather than the mean is about 94.5% as efficient as the t-test. So you're pretty close there. You're almost certainly going to get the same answer. Although if you have some extreme outliers, things will change considerably because the median does not, is not influenced by outliers. It's, you know, whereas the mean is in some cases substantially influenced by outliers. We wanted to talk about correlation coefficients. Those are very easy to set up and run. And they have minimal assumptions. There are 2 versions that we typically rely on: the Pearson correlation coefficient, which is a parametric version, and the Spearman correlation, which is considered a non-parametric version. Non-parametric means you aren't relying on as many assumptions, basically, or no, you're relying on no assumptions. But in this case, the Pearson is used when you have 2 continuous variables, interval ratio, and you have a linear relationship between the variables, and there are no significant outliers, because again, outliers, when you use a parametric version of a test, those they're weighted. It's a lever arm weighting sort of a technique where it weights the score by the distance of the value from the mean of your distribution. So we always want to look for outliers and fix them if we can. So the Pearson, if we go up here, we go down to correlate, bivariate right here. And by default, it's going to run the Pearson because that's by far the most common use of the correlation statistic. So if we say we want to correlate FEV, age, and height, those should all be substantially correlated, you would think. And we'll always check to see what kind of options we have. It will give you some descriptive statistics if we want, so we'll turn that on. And we're going to move these over here. So what it's going to give us is a matrix as output, which tells us the correlation between FEV and age right here. The diagonal will always be 1, obviously. but the FEV in age is 0.756, a pretty robust correlation. And the correlation between FEV and height is 0.868, again, a strong correlation. And you can see it also gives us significance p-values right here. What this is telling us, the null hypothesis is that the correlation is 0. So this is telling us that we're quite certain, p less than 0.001, that the correlation between FEV and age and the correlation between FEV and height is not 0. We're very certain. And you can see here, it also just by default gives us the correlation between age and height. 0.792, again, a very strong correlation. Any questions about that? So the Pearson is the parametric version of the correlation coefficient. And what it's looking at, we'll look at FEV and age here. So we can, you always run, when you're looking at correlation between continuous variables, you're always going to want to look at the data, produce a graphic, and that's very easy in SPSS. Am I going too fast? Are you okay? So you can use a chart builder, which is the wizard. Let me show you how to do it with the legacy dialogues that have been in place since day 1. So legacy dialogues, scatter dot. We have a lot of options here, but we're going to run a simple scatter plot. So we click on that option and define it as FEV on the y-axis, the vertical axis, where the output, the criteria, or the dependent variable typically is placed on the vertical axis against age right here. And we can obviously make this, I can label it by sex if I want to and make it more complicated, but for purposes of this, we run a straight linear correlation. This is what we get. So one of the assumptions I said is that there will be a linear relationship, that is a straight line relationship. We can, if you double click on these things, the graphical output, and in fact, the table output we've been looking at, if you double click, it puts it in an editable window like this. So I want to add a line of best fit to it like that. And I can attach a label, which gives me the regression equation for the two. I'm going to turn that off for now and apply that. And it gives me that. And it also tells me that what they call the coefficient of determination. This is the correlation coefficient squared, 0.57, the proportionate overlap between the two variables. What it tells you is that if you know age, if you have information on age, that you know 57% more about FEV than if you didn't have age. That is, your prediction of FEV would be 57% more accurate than if you didn't have knowledge of the subject's ages. So you can see that's a very nice linear relationship right there. Now, since I've got that up, let me show you, if we put this in the edit window again and we double click on the line, let's see the fit line. You see we have several different options here. We can fit a quadratic, which is a slightly curved line, or a cubic, which is more of a, you can see it's a more curved line, more extremely curved line. We can also do this, the less line right here. So if I do that, what it does is it looks, in calculating the relationship between age and FEV, what it does is it makes local adjustments, i.e. For relationships that it finds within close proximity to one another. So it gives us it gives us some information in terms of the actual relationship between age and FEV. And the reason I wanted to do that is to show you, we talked about the Pearson, the non-parametric version is the Spearman. Now the Spearman will work on Spearman correlation coefficient or Spearman's rho, RHO. We'll work on ordinal, interval, or ratio scale data. So we can also use it for purely ordinal data. And what it evaluates, rather than a linear relationship, is a monotonic relationship between two variables. So what it's assessing is the degree to which, as one value, the value of one variable increases, the paired value of the other variable also increases, but not necessarily in a linear fashion. So we tend to use Spearman when we have, well, certainly ordinal data, or we have badly skewed, badly behaved data. So to run that, we simply, right here, I'm going to turn off Pearson and I'm going to turn on Spearman right here. So that will give us the monotonic relationship for these variables. And typically it will be slightly less. But if I was concerned about the distributions of these data, or if I had a better example is if I have, these are continuous variables. These are not. These are categories I formed that are unequal because of the intervals I used to define them. If I had an ordinal variable, such as a categorical variable like this, I would then definitely run a Spearman correlation. And you can see it's slightly less because it doesn't capture as much information as does the continuous variable. So I was trying to come up with a way to illustrate what monotonic means. And this is as close as you can do with SPSS. As the variables, the degree to which the variables tend to increase or decrease, covary really, is the degree to which they covary together, but not necessarily in a linear fashion. So if there's any question about the your distributional normality or the metric on which the variable was measured, the conservative route is to report a Spearman's rho. It's reported as R sub S, R sub capital S, rather than a Pearson's correlation. Any questions? Okay, time is going by quickly. So I did ask Deb to upload this, so you'll have a record of the assumptions. So let me go on to analysis of variance right here. There are many ways in SPSS to run analysis of variance. The quick and dirty way, and it's a very nice way in terms of information output, is to go to compare means and then say one-way ANOVA. So we want to look at FEV as a function of grouping variables. So let's just look at each category right here. It has, I think, three groups in it. So we have some options here. We can run pairwise comparisons such that we can look at the difference between each each permutation of pairs. This will kick out descriptive statistics. I like the Welch test, and it will give you a very nice plot of the means. So let's run that one, and then we'll. Okay, so I've got 4 H categories, 5 or less, 6 to 10, 11 to 15, and greater than 15. And you can see I have considerably unequal ends. This gives me mean values right here for each of the groups. For FEV, it gives me what we call an overall omnibus test, which tells us basically there's something going on here. You have significant differences between at least 2 groups here. So, and then I turned on the Welch's test because the Welch's test is kind of a non-parametric version of the ANOVA. It doesn't pay so much attention to potential violations of assumptions. So I always like to look at it to the Welch's test. And then here finally are the multiple comparisons where in turn it compares each group to each other possible group. So 5 or less to 6 and 10, and you can see they're all highly significantly different right here. And you also get confidence intervals. right here. And it gives you the mean difference, the raw mean difference between each of the pairs of groups. And you'll notice if you look through this that, excuse me, these are, let's see. Yeah, I don't want to go there because it occurred to me there's one other thing I wanted to show you. Okay, so this is a mean plot of age category versus forced expiratory volume. Very nice differences between there. So let me show you one other thing here. I believe I can do this in here. Oh, very importantly, I want to turn on the homogeneity of variance test right here. And we'll run that. And you can see that's the Levine statistic again. You can see that we have violated the homogeneity of variance assumption. If this is p less than 0.001, then we have violated that assumption, which would suggest, depending upon the journal we're submitting it to, we might want to go in and consider addressing this topic with either a non-parametric version of an analysis of variance or pursuing a more complicated analysis, what we call a generalized linear model analysis. So I didn't go through the assumptions of the analysis of variance, so here they are. So what it assumes in order that the output be accurate is that the samples are drawn from normally distributed populations, that the populations have a common variance. That's the Levine statistic we just looked at. The samples are independent of each other. That is, the same subject does not appear twice in the data set. That the observations are randomly sampled and independent of one another, and that factor effects are additive. So if we had multiple factors in this, and we would have to go to another analysis to do that, that's probably for another day. But if I wanted to run a more complicated version of that, I might go to generalized linear models. And here I would run FEV versus, I might have age and height as continuous variables and sex as a fixed factor. What it means is that the contribution or the prediction of FEV by sex, age, and height, all of those components are additive. That is, that the contribution of age does not differ depending on whether it's male or female, or the contribution of height does not depend on male or female. That would constitute a multiplicative or interaction term. So the assumption of a simple ANOVA is that these are additive to one another rather than multiplicative. And finally, regression is a complicated one. But let me show you how to set that up. It has, as you can see, if you go through the PowerPoint, you can see there are a lot of assumptions: linearity, homoscedasticity, normality, etc. So what I did was give you just an example of each one of them right here, what we're talking about when we're looking for violations of assumptions. And let's just start that. Let's see. So let's say we want to do a linear regression, and there are many regressions we can do, as you can see. We'll do a simple linear regression. Simple means one predictor. We're going to predict FEV as a function of age, I think it was. Let me stick with the example here, height. So height right here. So height is the predictor variable. FEV, forced expiratory volume, is the criterion or outcome variable. So we can, as with the others, there are always options for each of these analyses. We want to see the confidence intervals, certainly. We want to see the Durbin-Watson statistic, descriptives, and certainly the collinear. Well, we don't need that for this example. but let me show you. And then this is where we test our assumptions right here. Some of them anyway. So you can turn on the histogram, normality, probability plot, which we certainly want. And then we're going to look at this to test homoskedasticity. And you also have the option of producing all partial plots. That is, for each predictor variable you might have in the equation, it will produce a separate plot. Right now we have only one predictor height, but let me show you how this works right here. Yeah, we'll stick with that. So what you're going to get is the linear regression equation right here with the intercept and then the coefficients associated with the predictor, both under standardized, these are in raw scores, and standardized in standard deviation units. And what this is telling you is that for each 1 year, 1 inch, yeah, I was using height. So for each 1 inch increase in height on average, FEV goes up 0.132 units. So it gives us the ability down here to look at the normality of the residuals right here, and they're very nicely normal. So we've met the assumption of the normal residuals from the analysis. And this gives us, let me see. Okay. So this is looking at, yeah, the homoskedasticity are the residuals normally distributed. This gives us a plot of the normality, the PP plot. These are the residuals from the 600 odd cases into the degree that they plot on top of a straight line drawn through the diagonal. That's evidence of residuals being normal. So it looks like we've met that assumption. And here, this one looks, what we're looking at here is we want to see if the residuals across the entire range of predicted independent variables are randomly scattered, i.e. a cloud of data such that if we look at this end of the distribution, it looks like this end of the distribution. So what we see here is that we've got a really nice random assortment of residuals where we have most of our data. The zero is, these are standardized, so it's the mean. So we have a nice random assortment near the mean, but when we get to the outer ends of the distribution, that these are not, they're not symmetric above and below zero, and they're just very, very sparse. And that's one of the problems with regression analysis. You know, if we're dealing with variables that are somewhat normally distributed, what that means is that at the ends of both ends of the distribution, we're going to have sparse data. So in terms of meeting this assumption right here, homoskedasticity, variance of residuals is the same for any value of X. That one is just very, very difficult to meet when you have, say, a normally distributed outcome variable. So, oh boy. Okay, does anyone have any questions about this? I've got just a few minutes, so let me just run through these because what I did was I generated some output and I saved it in here so you could refer to it later. But in terms of regression, we want to look at the evidence that there is a linear relationship between the predictor and the criterion, which we did earlier. We want to look at homoskedasticity. I plotted it slightly differently here, but what we want to see is that the distribution of residuals at this end of the predicted value is similar to the distribution at this end of the distribution. So this should be uniform across the entire range of predicted values. And you can see we've got some issues right here. Let me just check out. So that's how we check for homoskedasticity. Normality, we look at the PP plot, and that's a function of whether or not the residuals, that is the error terms from your model, are normally distributed. And again, to the degree that they track on the diagonal line, that's evidence of the residuals being somewhat normal. And then something we haven't talked about, which is a concern when you have several predictor variables that are highly correlated, in this case, potentially height and age, because as age goes up, height also tends to go up. So we look at that by running a correlation matrix just to get a sense of how highly how strongly our multiple predictors are correlated with one another. And when you see a correlation this high, that should give you pause, because it looks like there's a lot of redundant information, a lot of common information across age and height. And we're not concerned about our outcome variable. That's what we're trying to predict. No problem with sex right there. So you can look at that preliminarily, but the linear regression analysis also gives you a couple of indices right here. They're perfectly correlated with one another, but they measure the degree of multiclinearity, i.e. redundancy among your predictor variables, in the degree to which they correlate with your outcome variable. So one is called tolerance, one is called the variance inflation factor. And the variance inflation factor is the reciprocal of tolerance, so they're perfectly correlated. But the kind of the rule of thumb is that if the tolerance is less than 0.2, or the variance inflation factor is greater than 5, then multilinearity is problematic, and you have to address that. Because it's going to, when you have high multilinearity in a regression analysis, your standard errors, and as a result, your confidence intervals are not stable. They're not interpretable in some instances. And finally, when you're dealing with data that might be related to some sort of a series variable, such as time, SPSS gives you the option to look at what's called the Durbin-Watson statistics, which evaluates the correlation, what we call the autocorrelation, from one time period to the next. Now, in this case, we didn't have any time variables, but if you were doing a time series analysis where you were looking at repeated measures over time, it would be very important to examine the degree to which there was correlated error in your measurement across time periods, and that's what the Durbin-Watson is for specifically. And you can see that a value of 2 is no problem, and we had no problem with this one. But if it approaches 4 or 3.5 or 4, then you've got a problem, and you have misspecified your model basically. So you have to go in and probably include time as a variable in your analysis. There are multiple fixes for that actually, but we've run out of time. Do you have any questions? What I'd like to reinforce is, some of this is kind of complicated stuff. When you get to regression analysis, we just barely touch the surface. And when you when you are working with a multiple regression such as this, where I would be interested in the contribution of all of these variables to forced expiratory volume, I would need to look at all of my plots. And this is what you're looking at right here. So you've got a lot of things to interpret here. And any one of them can blow up on you. So if you're going to do something like this, consider giving me a call or meeting with me about this. The others are pretty easy. They're pretty straightforward, and it's hard to get tripped up with those, but regression is particularly troublesome. And not only linear, but logistic and polynomial and all of the others are cantankerous. Okay. So are there any questions? That was very quick.
So Dr. Bay, do we need to make sure we run the assumptions first before anything else, correct?
I think it's always a good idea to, you first run the assumptions and then you say, okay, I've got some severely skewed data here. I have some outliers and I have to deal with those. Or otherwise, if you run the analysis and then you look at the assumptions, that you're just going to have to go back and rerun the analysis in a different way.
Okay,
I mean,
great.
so yeah, I always start with the assumptions, at least to
Okay.
get a sense of the kind of data that I have.
Thank you.
Yeah. And if you run an analysis and have some output and you see something in there that puzzles you or you're concerned about, let me know. And I'd be glad to go over it with you.
Great. Thank you.
And as you saw, SPSS, it will run several hundred different analyses with multiple options, and you can customize the analyses pretty nicely in SPSS, but it's not plugging SPSS. It's one of many statistical packages that do the same thing. It just happens to be relatively easy to use. And it's the one that we have a license for. Okay, anything else at all?
Well, thank you, Dr. Bay. I just had one question. If anybody has any questions with SPSS or data analysis with their own data sets, would they be able to reach out to you for a little consult or help? I will definitely, let people know if you're open to that.
Yeah, and it doesn't hurt to try it yourself. You can't break it. So
Yeah, absolutely.
Yeah, but if you have any questions, let me know. And I've done this enough that I understand most of what it's trying to tell us.
You are the expert on campus, so.
Yeah, probably. There are other people who are pretty good with it, but I've probably used it longer than most people. Mm-hmm.
Well, thank you so very much.
Okay, thank you.
Okay.
And I will, what's our next meeting, Deb?
So we have a little problem with the next meeting. It was supposed to be on the 19th, and we had a talk. We had planned a talk on REDCap, which is a survey instrument.
Oh, yeah.
But Jane and Jeff had to back off because of their commitments with the IBRS, and they're swamped. So they don't think they'll be able to have something for us next. So in 2 weeks.
Okay.
So we're trying to figure. So yes, that kind of fell through.
Okay.
But it's if we do have something, it will be on the 19th.
Okay, thank you.
Thank you.
Thank you.
Okay, thanks. Okay, bye.